Okay, we'll talk about Pascal's triangle in just a minute. Let me just do a few of these. So x plus 1 to the 0 power, well, that's just 1. And if you see the top row there is 1. X plus 1 to the first power is 1x, or x plus 1. Let's see. Next row is 1 and 1, 1 and 1. Okay. If I FOIL this, so if x plus 1 squared, I actually get x squared plus, let's see, 2x plus 1. So I have 1, 2, and 1, 1, 2, and 1. Oh, that's interesting. If I went further, you can probably see where I'm going with this. X plus 1, sorry, that's 1 to the third power. I would get x to the third. I believe it's plus 3x squared if I actually were to multiply that out. Plus 3x plus 1. And you can see those are the same four coefficients you get here. So this is a way of, we're going to use this Pascal's triangle to kind of think about how tough that is. Like just third power. I'm not even going to fourth or fifth power yet. But I would have to actually get this answer, I would have to take x plus 1 times x plus 1 times x plus 1, right? I'd FOIL these two guys. I get x squared plus 2x plus 1, like we did a second ago. And then I'd have times x plus 1. Then I'd have to clam this, right? Multiply 6 times and eventually get to this. That's a lot of work for one problem. So this is a way of shortcutting it, is by using each row in the Pascal's triangle to generate those. So in other words, if I wanted to do x plus 4, x plus 1 to the fourth, sorry, I don't know why I could do that. I would look at the, let's see, 0 power is the first row, so first, second, third, fourth. This row will give me the coefficient, so this would be x to the fourth power plus 4x to the third power plus 6x squared plus 4x plus 1. As I go down by degree, fourth degree, third degree, second degree, that's a second degree, first degree, and 0 degree, I'm using those coefficients out in front, 1, 4, 6, 4, 1. It's just a very fast way of using this to generate the answers. Now you have to be able to continue the pattern here. I don't know if you see the pattern on this, but like you can see ones on the outside. That's pretty easy to see. And you might even see this, like the next number, 1, 2, 3, 4, 5, 6. That's 6. That makes sense. Same thing, this diagonal this way. This is 6. That's easy to see. Maybe hard to see this. 1, 3, 6, 10. I don't know. What's the pattern there? Maybe not as easy to see some of those other patterns. The way I prefer to see this is this way. 5 plus 1 is 6. 10 plus 5 is 15. 10 plus 10 is 20. 5 plus 10 is 15. 5 plus 1 is 6. Ones are always going to be on that side. Ones are always on that side. So to get the next term here, I'm taking these two terms, kind of adding them together to get 7, 21, 35, 35, 21, and 7. So each time you're adding a term, you're taking the two terms above it and adding to get that term. I did that funny, but that's the idea of it. And you'll generate it gets the next term. So if you know the first two rows of the binomial theorem, you'll be able to just continue that off and use that to solve our problem. So let's actually use this to multiply out. So for example, if I want to do a plus b squared, so that's, let's see, this is 0 power, this is first power, this is going to be second power. So I'm circling this row. So those are my coefficients. So what I do is I write 1, 2, and 1 out here. And so this is going to be, if I look at my a term, so my first term there is the a. So this is going to be, I'm going to start that with the highest degree term. So this to the second power. So a squared, a to the first. If I were to write a here, the last term would be a to the 0, which is really 1. I'm just going to leave it off instead. And then the second term is b. So because there's a second term, I'm going to start the last term with my highest degree. So b squared is the highest degree. B to the first is the next, and then b to the 0, which is really 1, is there. So, and then these are both plus. So I should get, if I FOIL those two, I should get a squared plus 2ab plus b squared. So that's, to the second power. Because again, it starts with 0 power, first power. These are the degrees. The second degree is second degree. Third degree, fourth degree, fifth degree. This one right here is fifth degree. So I'm going to leave myself a little more room here. So I get, let's see. So I'm going to take these coefficients, just kind of space them out. 1, 5, 10, 10, 5, and 1. Probably left a little more space in there, but we'll be okay. So the first term is to the fifth power, right? So a to the fifth, a to the fourth is the next term, a to the third, a to the second, a to the first, and then just constant or a to the 0 power. Next term is also to the fifth, but that's our last term, so I'm going to put b to the fifth, b to the fourth, b to the third, b to the second, b to the first, and then just a constant there. So I'm going to put pluses here. None of them seem to be negative, so I think we've got that. That would be our answer. You could simplify it slightly that you don't necessarily have to write the 1a to the fifth kind of thing, but that's how you use the Pythagorean theorem, or the Pascal's triangle, to expand. Now let's try a Telford version. When you have a negative in there, it's definitely going to be a little bit more challenging here. So let's figure out which one we're dealing with here. So this is third power. So 0 power, first power, second power, third power. So I'm going to circle this row because that represents the third power coefficients there. So I'm going to write out the 1, 3, 3, and 1. I'm just going to kind of space those out. The first term is x. Well, that's easy. That'd be x to the third, x squared, x to the first, and a constant. Careful, this is now negative 2. So I'm going to write it that way. So this last term is going to have a negative 2 to the power of 3. In parentheses, I'm plugging in with parentheses, negative 2 power 2, negative 2 power 1, just a constant there. And so all these are plus right now, but we'll see what happens when we kind of simplify this. So the final answer would be x cubed. Let's see, negative 2 would make this term negative, so minus, not 3, minus 6x squared. A negative squared is positive. That's a positive 4. 3 times 4 is 12, so plus 12x. Negative 2 and odd powers can be negative, so that's negative 8. So 1 times negative 8 is minus 8. So that is the expansion. So this is called, what we're doing is we are expanding binomials. Expanding. And we're using Pascal's triangle to expand binomials. And so this is the expanded version of this binomial to the third power there. A little bit tougher, again, trying to kind of layer it, order of degree of difficulty here. So 0 degree, first degree, second degree, third degree, fourth degree. So I need that row. So I'm take those coefficients, 1, 4, 6, 4, 1. So I'm going to take the first term, be careful, use parentheses, so to the x to the fourth power. So to the x to the fourth, 2x, sorry, 2x to the third, 2x quantity squared, and just plain old 2x there, and then the constant. Okay, negative 3 is being put to the fourth power, so that's to the last term, so I'm going to put it this way, negative 3 to the fourth, negative 3 to the third, that's a 3 there, negative 3 squared, and negative 3. And right now, all these are plus. We'll see if some of them become negative here, but I'm just going to put this in there. So this is 2 to the fourth, which is 16. So this first term is 16x to the fourth. That's not too bad. It's definitely going to be negative because of the negative right there. So I have 2 to the third, which is 8. 8 times 4 is 32. Times 3 is 96, I think. 96 x to the third. This is going to be positive, so plus 9 times 6 times 2 is 12. 9 times 12 is 108. This is x squared term. This is definitely going to be negative, so minus 8 times 27. Wow, 27. If I don't have a calculator, 27 times 8, 56. 5, 16 is 21. 216. So minus 216 x to the third. Oh, wait. Yeah, x to the third. Sorry. X is being put to the first power. Yeah. Fourth degree, third degree, second degree, first degree. That's just first power. It's going to be positive because of negative to an even power. Negative 3 to the fourth power, or 3 to the fourth power, is 81. So I'm adding 1 times 81, which is 81. And I believe that is our expansion of this binomial. It was a bit of work to simplify that, but it's a lot better than foiling that out, foiling out the other two, clamming that together. It's just going to take so many multiplying times when you do that. I think y'all are getting it, but let's do one more. So 0, 1, 2, 3, 4, 5. Uh-oh, I need the next row. So 1, 6, 15, 20, 15, 6, and 1. So those are what I need. 1, 6, 15, 20, 15, 6, and 1. So first term, this is not bad. This is just 2 to the sixth, right? 2, I'm not going to worry about parentheses. It's positive. Times 2 to the fifth, times 2 to the fourth, times 2 to the third, times 2 squared, the times 2 to the first, and then just constant there. Negative x to the sixth, so this is going to be negative x to the sixth, negative x to the fifth, going backwards, negative x to the fourth, negative x to the third, negative x squared, and just plain old negative x. Right now, there's just plus signs in between, and we're going to figure out if some of these simplify a little bit. So 2 to the fifth is 32, I think. 32 times 6. Wow, 32 times 6 is 12. 118 is 19, 192. So we have 180, negative 192x. It's going to be positive. Wow, we have 2 to the fourth. Okay, so you might have to pull out your calculator to do some of this. So I went ahead and did that. I did 2 to the fourth times 15, which is 16 times 15, which is 240. So it would be 240 x squared. This one's going to be negative because we have a negative to an odd power. And this is 20 times 8, which is 160. So 160 x squared. This is x to the third, actually. You can see it goes up x to the first, x squared, x cubed. It's going to have a pattern to it, so you'll catch your mistakes here. This is a negative to an even power, so that's going to be positive. 15 times 4, I think it's 60. X to the fourth. And then this is a negative to an odd power, so it's going to be negative. 6 times 2 is 12, so 12x to the fifth plus x to the sixth. And so when you think about it, like that would be a lot of multiplying. Any binomial to a sixth power would be a nightmare to actually multiply out. So this is much faster. It's just following that kind of a pattern there, and you can do this. And we'll talk about a project a little bit later on about how you could potentially do a coloring project if you want to get some extra credit points. That's a lesson for today.